Alright, this is LeetCode 797, all paths from source to target, given a directed acyclic graph DAG of n nodes, labeled from 0 to n minus 1, find all possible paths from node 0 to node n minus 1, and return them in any order. The graph is given as follows. Graph I is a list of all nodes you can visit from node I, i.e. there's a directed edge from node I to node graph ij. So if we look at this first example, this is the edge list for vertex 0. So we got an edge going from 0 to 1, 0 to 1, and 0 to 2, right? And we can say that here. For the second one, this is for vertex 1. We got an edge going from 1 to 3. For this is vertex 2. We've got an edge going from 2 to 3. And 3 has no edges outgoing from it. And as you can see, to get to endpoint 3, we can go from 0, 1, 3, or 0 to 3. Okay. For example 2, it's the same thing. We got this first vertex 4, 3, 1. So we got edges going from 0 to 1, 0 to 3, and 0 to 4. We have vertices 3, 2, 4. So we have edges going from 1 to 3, 1 to 2, and 1 to 4. For vertex 2, we just have a single edge going from 2 to 3. For vertex 3, we have a single edge going from 3 to 4. So, yeah, and these other examples are the same deal. You can draw them out accordingly. Okay, for our whiteboard here, we're going to go through example 1. We have 3 possible algorithms to go through. DFS, iterative, recursive DFS, iterative DFS, and BFS. And there's always 2 ways to write DFS, recursive or iterative. And I don't think there's a recursive version of BFS. So BFS is I think always iterative. Okay, so just a sec. All right, so let's keep going here. We're gonna start with res equals. I'm sorry. Okay, all paths equals an empty array, and we're gonna call a recursive DFS on current equals 0, current path is just starting from the 0 vertex. So, and then if 0 equals len of graph minus 1, we can see the size of the graph is 4. That means there's 4 vertices. The size of the input of graph is an array of 4 arrays. So that's going to be 4 minus 1. We know that that's not true. So we do else, and then 4I in graph of 0, and that's going to be our first element here, is 1, 2. And then we do DFS for I equals sorry, just a sec. Okay, so we do in this case I equals 1, cross that off, and then we do DFS 1, 0, which is the current path, plus 1. Okay, so those arrays are being concatenated together. So we do this, and then if 1, which is equal to I, equal to 4 minus 1, which it isn't, else for I in graph of current, which is 1, and that's 0, 1, 3. I'm sorry, that's getting ahead of myself. That's 3. And we know that from here, that's the second element here, right? So we do this, I equals 3, cross that out, and then that means we call DFS of 3 of current path, which is 0, 1, plus 3. Okay. So we do that. And then we do if 3 equals sorry, that's a really ugly 3. So this is true. Then we append to all paths the current path. 0, 1, 3. Okay, so 0, 1, 3 goes in there, and you can see that's what we have here. That's what we have right here. And then, okay, so this for loop ends. This for loop is done. Okay, and this and then this DFS returns. This DFS returns, and then now we go to I equals 2. Okay, so so we'll just do that, and I'll just erase this. Okay, I equals 2. And then that means DFS is called on 2 and the current path, which from this point is 0, right? And then okay, and then we have to add a 2. We have to add the current vertex 0, 2, right? And then we do DFS of, sorry, just a sec. Okay. So DFS of 2, 0, 2, and if 2 equals 3, then it doesn't, so ignore that, else for I in graph 2. And what is the second element, the second index element here? It's just this single array 3. So 3 we call DFS 3 the current path, which is 0, 2, and we add the current vertex 3. Okay. And then this goes to if 3 equals 4 minus 1, that checks out. Then all paths dot append 0, 2, 3. Okay, and that's our second element right here. So that's how you do the recursive DFS. Okay, let's keep going here. we're going to do the iterative DFS. We'll just go through it line by line. Line of graph, -1, 4 minus 1 equals 3. Let's go this way. Path stack, just a single vertex 0, and all paths is an empty array. So while path stack current path, pop off the the last element in the array, last element in current path equals 0. And this, when you do an array of index -1, you just get the last element in the array, and there's only one element in the array, and that's 0. And that's just going to be a 0. And then we do for neighbor in graph of last element in current path, which is 0, and that's, what's the first element of our graph? 1, 2. 1, 2. And so if 1, our neighbor is just 1 right now, it's the first element. So if 1 equals n, it doesn't. So we do else path stack dot append current path, which is 0, plus our current neighbor, which is 1. So here, okay, yeah. So yeah, we're currently processing the 0 right now, and we're going to put that next in line to process. And then for neighbor, we already processed the 1, so neighbor equals 2. If 2 equals 3, which it doesn't, else, I'm just going to start doing these in one line just to save space, limited space here. Else path stack dot append 0, 2. So to 0, 2, we add that onto the path stack. And that's all our neighbors that have been processed. And so we gotta go back up and iterate at the while loop again. So this stack frame disappears. Right? Okay. So our current path is 0, 1, last element of the current path is 1. And then for neighbor in graph of 1, which is 3, okay, if 3 equals 3, which it does, then all paths append current path to 0, 1, and a 3. You can see here that's our first path. Okay. And then, okay, there's only one element to process. And we've processed the 0, 1. So let's delete this stack frame. Okay, processing 0, 2. Current path is 0, 2. Last element is 2. Then for neighbor in graph of 2, and what's our second index? It's always 0 index, right? So our second index is just pointing to an array of single element 3. If neighbor, which is 3, equals 3, which is n, which is true, then all paths dot append the current path 0, 2, 3. Oh, I forgot to add the 0, 1, 3 here earlier. And then we're also appending 0, 2, 3. And then go back up to the while loop again. And okay, we already processed that last element, so the path stack is now empty. So we're all done. We return all paths, and that is our answer. And so that is the iterative DFS. The BFS is going to be the same thing, except we change the order in which we process the elements. So you notice this pop 0 here. We just have a pop parentheses for the iterative DFS. When you pop 0, you pop off what's in front of the. Oh, okay. I actually did the BFS version here because I was doing a first in, first out situation, and I was adding elements to our path stack, and I was processing them first in, first out. First in line is the first one that gets processed. For the DFS, we are popping elements off at the end, so I should have actually processed 0, 2 and then 0, 1. Because in DFS, we push an element onto the stack, we push, and then we pop on the very last element that got pushed. And then for a queue, we push elements, and we pop them off based on the first ones that got pushed. And so, sorry, I was actually doing BFS. Yeah. But yeah, for DFS, we would have added the 0, 2 on, and then we would have popped off the 0, 2, processed that. Then we would have popped off the 0, 1 and processed that. But we would have got the same answer anyway. We just would have added 0, 2, 3 first, and then 0, 1, 3. But I don't think the order in which you add the paths really matters. Okay. Thanks, guys.